Hey everyone, welcome to lecture 4.2. So we're going to be doing expected value and standard deviation for PDFs and of discrete RVs. So if you need to refresh on what a PDF of a discrete RV looks like, definitely check out the lecture video for 4.1. So we'll be carrying on today, moving into how to compute the mean or expected value and the standard deviation. So here we have the formula for our mean from a PDF. So we have that mu, our mean or expected value, is the sum of the data value x times the probability of x happening. So for this, we need a probability for every value. So let's start with an example here. A men's soccer team plays soccer 0, 1, or 2 days a week. The probability that they play 0 days is 0.2. The probability that they play 1 day is 0.5, and the probability that they play 2 days is 0.3. Find the long-term average or expected value mu of the number of days per week that the men's soccer team plays. So the first thing you want to do is you want to list all of the possible values. So for us, that was they could play, well, actually, let's do this first. So x is a random variable that represents the number of days per week that they play. Right, a men's soccer team plays soccer 0, 1, or 2 days per week. So x is just going to represent the number of days per week that soccer is played by these men. All right, so that's identifying the random variable. And now we're going to list all the possible values for that random variable. So they could play 0 times, 1 time, or 2 times a week. That's what the problem tells us. The next thing you want to do is you want to list the possible values probabilities, right? So the probability of the values. And we talked last time we can have P of little x or P of cap x equals x, and they both are the same. So the probability of playing 0 times 0 days is 0.2. So that's given to us in the problem. So that was here. Then we have the probability that they play 1 day is 0.5. So that's going to be here, 0.5. And then the probability that they play 2 days is 0.3. So that is going to go right here, 0.3. And remember that to be a PDF, we have to have all of our probabilities between 0 and 1, and they have to sum to 1. So 0.2 plus 0.5 plus 0.3 is 1. So we're good there. So next what we want to do is we want to multiply the value of the random variable by the probability itself. So that is to say, I'm going to combine the numbers, right? So I'm going to take this number and multiply it by this number. So I get 0 times 0.2, which is just 0. Then I get 1 times 0.5, which is 0.5. And then I get 2 times 0.3, which gives me 0.6. And then the last thing I need to do in order to compute my mean mu is I just add it up. So I get mu equals 0 plus 0.5 plus 0.6, which gives me 1.1. So the mean number of days this group plays soccer a week is 1.1, which is kind of a silly thing today to say, because we kind of think about this as a whole number, but this is the meaning of the expected value. So again, that's our expected value, mu, is the sum of all of the values x multiplied by their probability. All right, so if we want to compute the standard deviation for a PDF, we have a method for that as well. So just remember that we have a little bit of a different form for each situation. So when we're doing the population standard deviation, we're going to be dividing by n and dividing by n by 1. So that was kind of like a big idea when we first introduced this. We don't have to worry about that here because we lose the division in a sense. It's in there algebraically somewhere, but I promise I won't torture you with it. So notice that I still have x minus mu squared, right? So I'm still summing up these deviations squared. And then at the end of it, I'm still going to square root it. So we've got the similarities there. So last time we kind of just jumped, I think in chapter 2, we kind of just jumped straight into like, oh, it's a standard deviation. We also have variance, and they're very closely related. So variance is just that what we get right before we take the square root. So if we don't square root it, sigma squared, right, is called the variance. And the standard deviation is just the square root of the variance. So let's look at this same example, right, with the men's soccer team, and we will go ahead and compute. We're going to compute our variance, which is sigma squared, and we're going to compute also our standard deviation. So again, I don't want to rework everything that we had before. I know that mu is 1.1. I know that 0 times px gives me these values. So what I really want to do in order to compute my standard deviation is I need to find x minus mu squared. So in order to do that, I'm going to start with x minus mu, right? So this is our deviation. We've seen this before in 2.7. So this is going to be 0 minus mu, which was 1.1. So I get negative 1.1. Then I'm going to get 1 minus 1.1, which gives me negative 0.1. And then I have 2 minus 1.1, which gives me 0.9. So now that I have my deviations, I'm going to square them. So this is going to give me negative 1.1 squared, which is 1.21. Negative 0.1 squared is 0.01. And 0.9 squared is 0.81. Now the next thing I have to do, now that I have my deviations squared, before we would add these all up and divide by either our sample minus 1 or divide by the population. That's not what we're going to do here. We're going to take these and multiply them by their probability. So I'm going to take 1.21 and multiply it by 0.2, its probability, which gives me 2.42. I'm going to take 0.01, multiply it by its probability, right? So the 0.5. And that's going to give me 0.005. And then I'll take 0.81, multiply it by its probability, which should give me 2.43. All right, and I made a pretty crucial error on my decimal places. 0.242, 0.243. There we are. All right, so now that I have x minus mu squared by px, what I want to do is I just want to add them up. So now I'm going to get my total here. So this is going to be 242.242 plus 0.005 plus 0.243, and that gives me 0.490. I have to be very careful here because this should definitely be a lowercase x. All right, so now that I've added those all up, this gives me the variance. This is actually the variance. This is the very last step before we square root. So my variance here is 0.490. Then when I take the square root of that, I get 0.7. So my standard deviation is 0.7, which seems really high. All right, so that concludes the example for variance and standard deviation. So now let's do another example. Let's see how many examples we have. 1, 2, 1, 2. All right. So let's do another example. Suppose we have an experiment where we flip a coin 3 times, and then we're going to count the number of heads in these 3 flips, and we want to compute the mean and the standard deviation. So the idea here is first we have to identify the variables. So x is going to be the number of heads when flipping a coin 3 times. We're going to assume that this is a fair coin, and so that every coin toss occurs equally likely, like heads or tails, right? 50-50. So what are the possibilities that we can have, right? We can have, so this is kind of an interesting problem. We can have 0 heads, so we can have x equals 0. So if I have no heads, then that means I got tails, tails, tails. And what's the probability of getting tails, tails, tails? So this is going to be the probability that x equals 0. These are all independent events, right? So the probability of tails is 1/2. Then this next tails has probability 1/2. Then this next tails has probability 1/2. So that gives me 1/2 times 2 times 2, which is 1/8. So the probability for x equals 0 is 8. So I'm going to write this all out first, and then we'll put it into a PDF, and then we'll use it to compute our mean and standard deviation. So the next thing that can happen is that we can have 1 head, and this kind of happens in a few ways. So I can have a head on my first, meaning I get heads, tails, tails. I could get heads on my second trial, tails, heads, tails, or I could get heads on my third flip, tails, tails, heads. So heads, tails, tails, the probability of this is just the same. It's 1/2 times 1/2 times 1/2, right? It's 1/8. And the probability of tails, heads, tails is the same. It's 1/8. And in fact, for any particular triple flip, it's always going to be 1/8 because these are independent events with equally likely outcomes. So if I wanted the probability for getting 1 heads, I add these together, right? There is no overlap. These are mutually exclusive events. So the probability that x equals 1, it's 1/8 plus 1/8 plus 1/8, or 3/8. So that's not a coincidence. There's 3 ways to flip a single head. So that's 3 out of the total number of ways to flip a coin, 3 times. So we can kind of cut to the chase moving forward then, I hope. So let's do x equals 2. So for x equals 2, that means I get 2 heads. So I could get heads, heads, followed by tails. I could get heads, tails, heads, or I could get tails, heads, heads. So this is the exact same situation here, right? So I have a similar story to tell, and we arrive at the same conclusion. So the probability that x equals 2 is equal to also 3/8, right? Because the probability any one of these 3 rolls is 1/8. They are mutually exclusive events, and I have 3 of them. So summing them up, I get 3/8. So the last possible value I could get for x is 3. So the probability, or sorry, I'm looking at getting 3 heads. The only way to do that is just to roll straight 3 heads, head, head, head. So the probability of that is going to be 1/8 as well, just like the probability of tails, tails, tails was 1/8. So the probability that x equals 3 is 1/8. So now that I have this, I'm going to go ahead and construct my probability distribution. I think I'm going to, where should I put it? All right, I guess I'll put it here. So we have x, right? And we said that that could be 0, 1, 2, or 3. And then we had the probability of x, which was 1/8, 3/8, 3/8, and 1/8. So notice if we add those up, we get 8/8, which is 1. So that's good there. All right, so now I need to compute the mean. So the mean is just the sum of the data values times the probabilities. So for mu, I have to get, right, I need x times px. So this is 0 times 1/8, which is 0. Then I have 1 times 3/8, which is 3/8. Then I have 2 times 3/8. So yes, I could reduce this to 3/4, but I'm not going to. I'm going to leave it as 6/8 because I have to add all these up. So it's nice if they have a common denominator. And then I get 3 times 1/8 again, which gives me 3/8. So mu is going to be 0 plus 3/8 plus 6/8 plus 3/8. And so that gives me 12/8. Right? So I could think about that as 3/2 or 1.5. So the idea here is that if you toss a coin 3 times, we would expect to get 1.5 heads, which again sounds really easy, it's like silly, but that's just the way that expected value works. It's the long-term average. So now what I want to do, now that I have mu, I want to compute my deviations, x minus mu. So that's going to be 0 minus 1.5, which gives me negative 1.5. Then I have 1 minus 1.5, which gives me negative 0.5. 2 minus 1.5, which equals 0.5. And then 3 minus 1.5, which equals 1.5. All right, so that's my deviations. The next step is to square them. So I'm gonna get negative 1.5 squared, which gives me 2.25. 0.5 squared, 0.5 squared gives me 0.25. Right? Be it positive or negative 0.5. When I square it, they'll both be positive and they'll both be 0.25. And then similarly, 1.5 gives me 2.25. So now I'm going to multiply this x minus mu squared times p of x. So now I'm multiplying my deviation squared by the probability. So that's 2.25 times 1/8. 0.25 times 3/8, 0.25 times 3/8, and 2.25 times 1/8. So that gives me so just converting those into decimal form, I get the following values. So this tells me, so if I sum this up, if I take sigma x minus mu squared times the probability of x, this is my sigma squared. This is my variance. I just need to add these up. So if I add those up, oh, I forgot a little 2 in there. Hopefully I did this right. So I got, when I sum them up, $0.571289. And I'll just leave it right there. Let me just see if it makes sense. So 56 and 8. Yeah, okay. I will believe this. Right? I believe that. Nope, I don't believe that. I know what I did. .75. Right, so you get 56, 18, 74 plus change. All right, much better. So 7.75 is our variance. And then all I do to get the square root is all I do to get the standard deviation is I just take the square root of that. So the square root of 0.75 is 0.866. Right, so we've got our variance, we've got our standard deviation. And then we also had mu. So we found all the things that they wanted us to find, right? So we've got mu, 1.5. We've got our variance, 0.75. And then we've got our standard deviation, 0.866. And of course, you know, we have to be mindful of how many decimal places they want, but this is the method of how it's done. All right, here's the last example. This one's a bit more interesting, especially if you like gambling and the lottery. So, all right. The cool thing about gambling is either on any given hand, you either won or you didn't, right? You either paid the house or the house paid you. So the Ohio Lottery has a game called Pick 4 where a player pays $1 and picks a 4-digit number. If the 4 numbers come up in the order you picked, then you win $3,400. So what are all the ways that you could pick 4 numbers, right? So in any 4-digit number, you could be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? So you have 10 choices here. But we could repeat a number. It doesn't say we can't repeat. So we also have 10 choices here. And 10 here, and 10 here, right? And so on. So if I wanted to know how many ways I could pick a 4-digit number, all I have to do is I'm just going to take 10 and multiply it together 4 times. So how many ways to pick a 4-digit number? It's 10 times 10 times 10 times 10. Did I say that 4 times? It's 10 4 times multiplied together. So that's 10 to the 4th. Another way of writing that is a 1 with 4 zeros. Right? So there's 10,000 ways that you could choose a 4-digit number. So now what happens? Let's say the probability that you win. So what is the probability of picking the winning number? So there's one winning number and you have 10,000 ways that you could pick that number, right? So the probability of winning, right, is 0.0001. So if you pick the right number, then you win. So the probability of winning equals 0.0001. So let's talk about losing a little bit. Right? The probability of picking the wrong number. Well, there's 9,999, sorry, yes, no, that's correct, wrong numbers out of 10,000 total numbers. And so you're going to get a 0.9999 is your probability of losing. So probability of losing equals 0.9999. So it's not looking good for you, but you know what? It only cost $1. So let's talk about what our variable is. Our variable is the amount of money won or lost, right? So if I win, so let's set up our table. And this might feel a little counterintuitive, but let's start with the winning and the losing. Two things happen when you play the lottery. You win or you lose. So I'm going to label this guy win, and I'm going to label this guy lose. If you lose, let's start with the losers. If you lose, how much money did you lose, right? Well, it cost $1 to pay. Oh my gosh. It cost $1 to play. So if you lose $1, right? So our X value is -1, the amount of money won or lost. I lost $1, so I'm going to write that as -1. And the probability that I lose is 0.9999. If I win, how much money did I gain? Well, I'm going to win $3,400, but it also cost me $1 to play. So this is really 3399, right? It's that 3,400 minus $1, that dollar that you spent to play the game. And the probability of winning is 0.0001. All right, so now that we have that set up, we have our PDF set up, let's figure out what the expected value is. So our expected value is the sum of our x times px, right? So that's 3399 times 0.0001. And then we also have to do -1 times 0.9999. So second one's easy. I could do that in my head. -0. And then this one, I move it over 4. Bop, 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 bop. I find it's easier to do mental math when you make noises, but I'm also going to double check on my calculator. 3399 by 0. Okay, I'm just making sure I'm not losing my mind over here. So now we have our x times our px. And what we want to do is we want to just compute our mean. So mu, our mean or expected average, is 0.3399 plus -0.9999. And so if we take that, we're going to get -0.66. So think about this from your standpoint. You pay $1, and over the long term, you expect to lose, 0.66 cents per every time you play. If you're the lottery, right? If you're the Ohio State Lottery, you have all these people on average losing 66 cents every time they play. So you're just like raking in the dough. So next time you're like, man, how can they like afford to give out such high winnings? They're fine. They are just fine. Don't worry, they have all your money, and you know it, and I know it, and they know it. All right, so if we wanted to compute, I don't really want to compute the standard deviation on this because we only have 2 data points. So I'm just going to leave it as the expected value. And that's actually my last example for this lecture. Next lecture, we're going to be talking about the binomial distribution, which will flow nicely from this. So good luck out there. Don't play the lottery.